January 15, 1943. Rostov, Soviet Union. Temperature, minus 22 degrees Celsius. Unteroffizier Hans Weber, a 26-year-old tank mechanic with Schwerpanzerabteilung 502, stared at the Tiger Eye that had broken down for the third time in 2 weeks. The problem wasn't enemy fire, it was the overlapping road wheel design. To replace the inner wheels, Weber and his crew had to remove up to 20 outer wheels first, a job requiring 16 hours in perfect conditions. In the Russian winter, with frozen bolts and limited tools, it took 3 days. The Tiger's final drive, meanwhile, had failed after just 150 kilometers, a fraction of its design specification. Weber wrote in his maintenance log, "This tank is a masterpiece when it runs. But it runs so rarely that we spend more time repairing it than fighting with it. We joke that for every hour the Tiger fights, we spend 10 hours fixing what breaks." The Tiger Eye's reputation as an invincible battlefield monster masked a truth that mechanics like Weber understood immediately: brilliant engineering had created a maintenance nightmare that crippled German armored operations. This is the story of the fatal flaws that made the Tiger tank as dangerous to its own logistics as it was to enemy forces. The Tiger Eye entered service in August 1942 as Germany's answer to Soviet heavy tanks. On paper, it was magnificent, 88mm main gun that could penetrate any Allied tank at ranges exceeding 2,000 meters, frontal armor up to 100mm thick that was effectively immune to most Allied anti-tank weapons, powerful Maybach HL-230 engine producing 700 horsepower. In combat, when it worked, the Tiger was devastating. A single Tiger could hold off entire tank battalions. Allied tank crews feared it. But the Tiger's designers at Henschel had prioritized firepower and protection while accepting compromises in reliability and maintainability that would haunt German panzer units throughout the war. 3 design decisions created the maintenance nightmare. First, the overlapping road wheel suspension. Henschel used overlapping steel wheels to distribute the Tiger's 56-ton weight across a wider track surface, improving cross-country mobility. But this meant wheels were layered 3 deep. When an inner wheel broke or its bearing failed, common in Russian mud and cold, mechanics had to disassemble the entire side to access it. Second, the final drive. The transmission transferred power to the drive sprockets through final drive units that were chronically underpowered for the Tiger's weight. They failed regularly, often within the first few hundred kilometers. Replacing them required removing the entire front hull plate, a major workshop job impossible in field conditions. Third, overall complexity. The Tiger required specialized tools, trained mechanics, and workshop facilities that simply didn't exist at the front. The overlapping road wheel design, called Schachtel-Laufwerk in German, seemed brilliant initially. Each Tiger had 24 road wheels per side, arranged in 3 overlapping rows of 8. This distributed the tank's massive weight efficiently and provided excellent cross-country performance. The wheels were steel with internal rubber cushioning, no rubber tires that could be damaged by gunfire or cold. But the design created cascading maintenance problems. In muddy conditions, mud packed between the overlapping wheels and froze solid overnight in Russian temperatures. Crews had to spend hours each morning chipping ice from between wheels before the Tiger could move. If they failed to do this, the frozen mud could jam the suspension or crack wheels as the tank tried to move. In dry, dusty conditions, fine dust infiltrated the wheel bearings, causing premature wear. The bearings had to be repacked with grease regularly, a job requiring partial disassembly of the wheel assembly. When a wheel or bearing actually failed, the maintenance nightmare began. To replace an inner wheel on the first row, mechanics had to remove 9 or 10 outer wheels, disconnect the track, lift off the outer wheels one by one, access the damaged wheel, replace it, then reassemble everything in reverse. With a full maintenance crew and proper tools, this took 16 to 20 hours. In field conditions, with improvised tools, frozen bolts, and mechanics working in sub-zero temperatures, it could take 3 to 4 days. Hans Weber's maintenance logs from early 1943 document the practical impact. His unit, Schwerpanzerabteilung 502, received 9 Tigers in November 1942. By February 1943, only 3 were operational at any given time. The others were deadlined for maintenance, primarily wheel and final drive problems. One Tiger had been immobilized for 6 weeks waiting for a final drive replacement that had to be shipped from Germany. Weber recorded a typical incident on January 22. Tiger 231 through a track during movement to combat position. Inspection revealed inner road wheel failure on right side, 8th position. Began wheel replacement procedures 0800 hours. Required removal of 10 outer wheels to access damaged wheel. Frozen bolts required heating with blowtorch, dangerous near fuel tanks. Completed wheel removal by 1600 hours. No replacement wheel available. Cannibalized wheel from Tiger 234, already deadlined for final drive failure. Reassembly not completed until January 24 due to frozen track pins. Total time, 56 hours for single wheel replacement. Tank missed 3 days of combat operations. This wasn't exceptional, it was routine. Soviet and Allied intelligence reports from 1943 to 44 consistently noted that German Tiger units operated at 30 to 50% strength, not from combat losses, but from mechanical breakdowns. American technical intelligence assessed captured Tigers and noted, the overlapping wheel design provides excellent mobility when functional but creates maintenance requirements far exceeding field repair capabilities. This is a critical vulnerability. The final drive problem was even more critical. The Tiger's final drive units transferred power from the transmission to the drive sprockets that moved the tracks. Henschel designed these units for a tank weighing 45 tons. The production Tiger weighed 56 tons, 25% heavier. The final drives were chronically overloaded and fail regularly. Early production Tigers experienced final drive failure after an average of 150 kilometers, less than 100 miles. Even after modifications improved reliability, final drives rarely lasted more than 500 kilometers before requiring replacement or major overhaul. The replacement procedure was the ultimate maintenance nightmare. The final drives were mounted inside the front hull, accessible only by removing massive armored front plates. This required lifting the 56-ton tank with specialized jacks, removing the track and drive sprocket, unbolting and removing the entire frontal armor plate, which weighed over 300 kilograms, extracting the failed final drive, installing a replacement, then reversing the entire process. This was a workshop job requiring overhead cranes, precision tools, and trained specialists. It was completely impossible in field conditions. When a Tiger's final drive failed in combat areas, the tank was immobilized until it could be recovered to a rear area workshop, often hundreds of kilometers away. Recovery itself was problematic. The Tiger was too heavy for standard German recovery vehicles. It required multiple SDKFZ-9 heavy half-tracks working together, and even then recovery was often impossible if the Tiger was stuck in mud or under enemy fire. The consequences extended beyond individual tanks to entire operational planning. German commanders quickly learned they couldn't use Tigers the way they used other tanks. Standard Panzer doctrine emphasized mobility, rapid advances, flanking movements, exploitation of breakthroughs. The Tiger's maintenance requirements made this impossible. If a Tiger unit advanced 50 kilometers in a day of combat, modest by Panzer standards, approximately 20% of its tanks would break down from the strain on final drives and running gear. If the advance continued, war Tigers would fail daily. Within a week of sustained operations, an entire Tiger battalion could be scattered across hundreds of kilometers, broken down and awaiting recovery. Instead, German tactical doctrine evolved to use Tigers defensively or in limited, carefully planned offensives with extensive maintenance support pre-positioned. Tigers would advance to prepared positions, fight from those positions, then withdraw to workshops for maintenance before the next operation. This negated much of armor's traditional advantage, mobility and exploitation. It turned the Tiger into what one German commander called a mobile pillbox, effective when stationary, nearly useless when required to maneuver. Major Richard Marker, commanding officer of Schwerpanzerabteilung 503, wrote in his after-action report from Kursk in July 1943, of 45 Tigers committed to Operation Citadel, only 17 remained operational by day 3. 23 were deadlined for mechanical failures, primarily final drives and wheel assemblies. 5 were total combat losses. Our maintenance companies are working around the clock but cannot keep pace with breakdown rates. The complexity extended to every system. The Tiger's engine was the Maybach HL230P45, a powerful and sophisticated V12 producing 700 horsepower. It required high-grade fuel, increasingly scarce as the war progressed. It consumed 500 liters per 100 kilometers on roads, more in combat conditions. A Tiger's fuel capacity was 540 liters, giving it a theoretical range of barely 100 kilometers. In practice, combat operations consumed fuel far faster. A Tiger advancing cross-country under combat conditions might cover 30 to 40 kilometers before requiring refueling. This meant Tiger units required massive logistics support, fuel trucks constantly supplying forward positions, spare parts convoys, maintenance personnel that outnumbered tank crews. For every Tiger crew of 5 men, the Schwerpanzerabteilungen required approximately 15 maintenance and support personnel. The Tiger's transmission was equally problematic. The Maybach Ulver OG 4012-16B was a sophisticated preselector gearbox, advanced for its time but mechanically complex. It required careful operation and regular maintenance. Undertrained drivers, increasingly common as the war progressed and experienced tankers were killed, would damage transmissions through improper shifting. Transmission failures required removal and workshop repair, another job impossible in field conditions. Spare parts were chronically short. The Tiger was produced in limited numbers, only 1,347 Tigers built during the entire war. This meant spare parts production was also limited. When a final drive failed, there might not be a replacement available anywhere in the theater. Mechanics resorted to cannibalizing parts from other damaged Tigers, which meant one breakdown could result in multiple tanks being deadlined. Hans Weber's experience exemplified the frustration of Tiger mechanics throughout the war. In his memoir written after the war, he described the psychological toll. We loved and hated the Tiger simultaneously. When it fought, it was invincible. I saw one Tiger destroy 11 Soviet T-34s in 20 minutes at Rostov. The crews felt like gods in those moments. But then we mechanics had to keep these monsters running. Every night was maintenance. Every morning was repairs. We scavenged parts from destroyed Tigers, improvised solutions with whatever materials we could find, worked in conditions where touching metal barehanded meant frostbite. The Soviet tankers feared Tigers. We feared breakdowns more than combat, because we knew breakdowns were inevitable and we were the ones who had to fix them in impossible conditions. The Wehrmacht attempted to address these problems. By late 1943, special Tiger maintenance companies were formed with enhanced equipment and trained specialists. Mobile workshops were developed. Procedures were streamlined. But these improvements came too late and were too limited. The fundamental design flaws couldn't be fixed without completely redesigning the tank. The Tiger II, King Tiger, introduced in 1944, addressed some issues but created new ones. It was even heavier, even more complex, and even less reliable. Actual combat statistics reveal the maintenance crisis's impact. Of approximately 1,347 Tiger is produced, German records show that roughly 65% of all Tiger losses were not from enemy action but from mechanical breakdowns that resulted in abandonment. Tigers broke down, couldn't be recovered, and had to be destroyed by their own crews to prevent capture. This wasn't because the enemy destroyed them, it was because they couldn't be maintained in field conditions. The maintenance burden affected German armored operations strategically. Each Tiger unit required a logistics tail far exceeding normal panzer units. A standard panzer battalion with panzer IVs needed approximately 200 support personnel for 50 tanks. A Schwer Panzerabteilung with 45 Tigers required over 600 support personnel, 3 times the ratio. These support troops included specialized mechanics trained on Tiger systems, recovery units with heavy equipment, supply personnel managing the flow of spare parts, and workshop companies capable of major repairs. All of these resources were diverted from other units. Every mechanic assigned to a Tiger battalion was a mechanic unavailable to support 3 or 4 normal panzer battalions. Every recovery vehicle dedicated to Tigers was unavailable for other purposes. The Germans were accepting a 3-to-1 support burden for tanks that spent more time broken down than fighting. Some German commanders questioned whether this was worthwhile. General Heinz Guderian, Inspector General of Panzer Troops, wrote to Hitler in 1944 arguing that resources spent on Tigers would be better used producing 3 times as many Panzer IVs or Panthers. The Panzer IV, though less powerful than the Tiger, was reliable, easy to maintain, and could be kept operational in field conditions. 3 Panzer IVs might accomplish more than 1 Tiger that spent half its time deadlined. Hitler refused. The Tiger's propaganda value, the psychological impact of an invincible supertank outweighed practical military considerations. Production continued even as mechanics at the front struggled to keep existing Tigers operational. Individual mechanics developed remarkable improvisations to keep Tigers running. Weber's maintenance logs detail dozens of field-expedient repairs, using wood blocks to shim broken wheel assemblies, fabricating replacement parts from salvaged materials, bypassing failed systems to keep tanks marginally operational. One entry from March 1943 describes replacing a failed final drive bearing with a bearing salvaged from a destroyed Soviet tank. The Soviet bearing was wrong specification but correct diameter. Machined adapter sleeve from damaged track pin using improvised lathe. Installed bearing with adapter. Not to specification but functional. Tiger 231 returned to operation after 11 days deadlined. Expect bearing to fail within 200 kilometers, but better than complete tank loss. This kind of improvisation was common but couldn't solve fundamental design problems. The overlapping wheels couldn't be simplified in the field. The underpowered final drives couldn't be strengthened without factory modifications. The complex transmission couldn't be made simpler through field maintenance. By 1944, the situation had become critical. Allied bombing had destroyed much of Germany's specialized manufacturing capacity. Spare parts production dropped while Tigers continued breaking down at steady rates. Workshop facilities were overloaded. Some Tigers sat deadlined for months awaiting parts that would never arrive. The mechanics were exhausted, working 16-hour days, constantly moving to avoid Allied air attacks, operating with inadequate tools and equipment. Many suffered from what we'd now recognize as combat fatigue, not from fighting but from the endless, hopeless task of maintaining machines designed without adequate consideration for field maintenance. The Tiger's maintenance problems offer lessons that echo in military procurement today. The tank was a marvel of engineering, powerful gun, heavy armor, sophisticated systems. But it was engineered without adequate consideration for practical field maintenance under combat conditions. Designers prioritized performance over reliability, complexity over maintainability, battlefield effectiveness over logistical sustainability. This created a weapon system that was tactically superior but strategically flawed. Modern military analysts studying the Tiger identify multiple design decisions that should have been challenged: overlapping wheels that were maintenance intensive when simpler suspension would suffice, underpowered final drives that failed predictably, complexity that required specialized support unavailable at the front, weight that exceeded recovery capabilities. Each decision made sense in isolation. The overlapping wheels improved mobility, the sophisticated transmission provided better control, the heavy armor ensured survivability. But collectively, they created a tank that couldn't be sustained in actual combat operations. By war's end, only approximately 120 Tigers remained operational from 1,347 built. Most hadn't been destroyed in combat, they'd broken down and been abandoned when recovery and repair proved impossible. Hans Weber survived the war. He returned to Germany, became an automotive mechanic, and spent decades working on civilian vehicles. In interviews late in life, he reflected on his Tiger experience. People remember the Tiger as this invincible monster. They forget we spent more time fixing them than fighting with them. The Tiger could have won battles if only we could have kept them running. But we couldn't. The design ensured that. It was a tank designed by engineers who'd never had to maintain one in mud, snow, and chaos. Beautiful engineering. Terrible design. Those of us who had to keep them operational understood the difference. Today, fewer than 10 complete Tiger I tanks survive worldwide, preserved in museums as testaments to both engineering ambition and the limits of over-engineering. The most famous Tiger 131 at the Bovington Tank Museum in England is the only operational Tiger remaining. Museum staff who maintain it understand Weber's frustrations intimately. Even with modern tools, proper workshops, and no enemy fire, keeping a Tiger operational requires constant maintenance attention. The overlapping wheels still create access problems. The final drives still require careful monitoring. The complexity still demands specialized knowledge. The Tiger represents a cautionary tale in military procurement. The most powerful weapon is worthless if it cannot be sustained in actual operations. German factories produced 1,347 Tigers at enormous cost in resources, skilled labor, and production capacity. Had those same resources produced 3,000 or 4,000 simpler, more reliable tanks, German armored forces might have been more effective overall. The maintenance burden didn't just affect individual tanks, it consumed support resources, exhausted personnel, and reduced overall German armored capability. For every Tiger kept operational through heroic maintenance efforts, several other German units went without mechanics, spare parts, and support equipment. The fatal flaw wasn't any single design decision, it was the accumulated effect of prioritizing performance over sustainability, sophistication over maintainability, engineering excellence over practical usability. The mechanics who struggled to keep Tigers operational understood this intimately. They deserve to be remembered not as footnotes to tank battles, but as the men who dealt daily with the consequences of design decisions made in peacetime engineering offices. Their story reveals a truth about warfare: battles are won not just by the best weapons, but by weapons that can be kept in the fight. The Tiger was the best tank of its era when it ran. But it ran so rarely that mechanics like Hans Weber spent the war fighting a losing battle against mechanical breakdown, armed only with wrenches, determination, and increasingly desperate improvisation. This story deserves to be remembered, not to diminish the Tiger's tactical effectiveness, but to understand why strategic brilliance requires more than engineering excellence. It requires sustainable, maintainable weapons systems that mechanics can actually keep operational under the chaos of combat. The Tiger tank, for all its fearsome reputation, failed that fundamental test.